Hello everyone, thank you for attending my talk. As you said, unfortunately my colleagues couldn't make it. Some of them are children, wives, you know the problem. So I am Raphael, but you really need to keep in mind that that's really a group project, and that was started by Sarah, who is the mastermind behind abstract interpretation, so you will see that later. Just a word before my talk. So the tool is available. It's open source. I will give you the link at the end. So I will introduce BinCAT to show you what it's about. Then go a quick demo to show you how to use it and what we can do with it. Of course, we'll go under the hood to see how it works, what we can do, and we'll conclude with some future work that we are going to do. So, a word of introduction, BinCAT is a binary analyzer. So the goal is to analyze binary code, so programs for different architectures. The main point is that it's a static analyzer. So at no point you are going to run actual code from the binary on the CPU. Everything will be done by the analyzer, and you will not be attacked by the code directly. For now, we support x86 32 bits. Well, we'll go back later into why we don't support other architectures yet. And so the goal is to analyze x86 code, and we support, the idea is to compute properties over the code we analyze. And we can analyze several things at the same time. So the first one that is very important is values. So we compute values for register and memories. We're able to track the register values and memory over the execution, so static execution of the program. We can also run taint analysis at the same time, bit level taint analysis, so we can show, try to see how data is used and follow the data flow for a particular register or memory. We'll see that with an example. Also, since we can do value analysis, we can track the value in memory in registers. And so while we reconstruct the control flow graph for disassembly, we are able to use the value analysis to reconstruct the indirect jumps that you can have. So for example, if you have an indirect call differencing memory or using a register value, then the analyzer should be able to compute the value and follow the indirect call. And we can also recover some types. We'll see that later. The analysis can be run in two modes. So we can run in forward mode, that is mandatory because you need to discover the control flow graph. So we'll run from the entry point and run the analysis forward. But then you may want to see, for example, at the end of the analysis, some variable that you're interested in. You could add some taint and then run a backward analysis to find where the taint could come from. That will give you a backward data flow analysis. One thing that we really wanted to make useful is we know that reversers are lazy. I am a reverser, I am lazy. So I want to do everything in IDA. I don't use Radari. Nobody uses Radari actually, so it's only in IDA, sorry. We'll see that if you want, you can write a Radari plugin to integrate with BinCAT, but well. So we want to make it easier, so we have an IDA integration with a guy, and you'll see that the pictures is pretty easy to use. And an interesting point is that we have Sarah, who is from an academic background, and she's very good. So she wanted to make something that is really sound. So we didn't like run around and do things randomly. We have a strong theory to back everything that we do, and I will go back on that later. And finally, we wanted to make BinCAT extensible. So to make it easy to add new things. The first one is that, of course, we don't analyze x86 directly. Nobody does that. So what we did is add a new intermediate language, of course, a new one, to support x86. And the analysis runs on the intermediate language and not directly on the x86 code. So if you want to add a new decoder, you only have to write the decoder to get your intermediate language, and then you run the analysis. And you can also extend the properties. So the properties can help each other, and all the computations that are done in parallel. So as I said, for example, values help for the CFG, but you could add anything you want. So that's nice, but a demo is always better to understand what we're talking about. So we made a small example, a toy example that covers some features of BinCAT that we wanted to show. So it's a simple Kijimi. I guess a lot of you have done Kijimis before. This one runs on Linux. You just have to find the right license that for the company, department, and name, so usual thing. If you give it a wrong serial, it will show you wrong serial. Since we have a toy example, we also display the valid license, so we can copy paste it and show another code path. So if you copy paste the right license, you run the tool again, you will get thank you for registering. So how does the license verification work? Here is the data flow that we will try to see with BinCAT. So it takes the 4 arguments, including argv, then it computes for each of the arguments a custom CRC32. 2 of them are not used. We won't have the time to show why we added that, but that's one of the points of BinCAT. The 2 of company and names are multiplied together, formatted using sprintf as a next string, then combined with another sprintf as a big string with all the arguments. This is input is passed to a SHA1 hash function. I know it's outdated and not secure, but that's a toy example. So SHA1 formatted as X, and that's a valid license. So keep in mind that the company and name are multiplied together, and we have a sprintf. So I'm going to show you a video demo because that's easier for you to see. If it works, it's better. Okay. So we have IDA here, pretty familiar with it, but if you look closely on the left, you have 3 panels that we added that are for BinCAT. So they will be there to show you all the information that BinCAT has computed over the binary. Here we want to analyze from the main function of the toy example that I've shown before. So we put the cursor at the first instruction of the main function, then we run the tool with a shortcut. A configuration dialog pops up. It presents you with options that you can configure the analysis. Here we will start with a completely new configuration. So when you click new configuration, the IDA plugin actually generates a new configuration for BinCAT from the information available in IDA. And here you can see everything that is passed to the analyzer afterwards. So first, here we have a Linux binary. And since BinCAT is able to support segmentation, we need to provide the GDT so that the analyzer knows where to look for data and code. So that's the default Linux GDT. But that's not the most important part. The most important part is this one. So here is the default initial state. Because when you run an analysis, you start at a point, but you have no idea what the register values are, what is on the stack, and whatever, because you cannot run the code. So here you need to supply the analyzer with an initial state so that it can run the analysis. Of course, you will supply the entry point because you need to start somewhere, but you also specify the registers. Here, we use for most of the registers a special value that is unknown. So we say, okay, we don't know what's the register value, but this register will be able to take any value. So that's why we have question marks here. We'll see that in the GUI later, that you can see that clearly. And then the only register that we actually define is ESP, because if you don't define a stack, nothing will work because you push and pop, so it won't work. Here in our example, of course, we want to run besides the usage that will show enter your serial or whatever. So here we paste the configuration that is exactly as if we were running the binaries with 5 arguments. So we'll see in the memory later that we just pass some strings as arguments. And finally, at the end of the configuration, you have the imports. So IDA recognizes the imports and they are passed to the analyzer because the analyzer needs to know when it's calling an external library, because the analyzer is static. So if you don't have the library, or if you don't know that it's an external library, it will not be able to continue. So we'd save the configuration. And we run the analysis. So it asks for a name. You have some tools to handle configuration. Then the analysis runs for a few seconds. And you will see that once the analysis is done, on the right, you have the disassembly window, and all the instructions that have been analyzed by BinCAT will be colored in gray. So on the right, everything has been gray. And you can see maybe on the left that everything is question marks except ESP. So that's where the enter point. So that's the initial configuration that we define using the text window that you saw. So you see that everything is unknown. That it means everything could be there except ESP. But we can check at the end that we have the actual argc argv that we specified on the stack. So here you have argc being 5 and the pointer, and then you can look for in memory for the other pointers, and then you can go and check the actual strings that are passed as arguments. So if you remember in the data flow of the keygenme, we have a sprintf that is used to format some strings. So we are going to see what did BinCAT recover from the sprintf call. So here we format the string in a buffer, just saying company equal something, the company that you specify. So remember that no actual instruction is executed on the CPU. So you need to, the analyzer needs to recognize that it's a sprintf and do something. So what is done here is that in BinCAT we have re-implemented a part of the sprintf call, and it's actually doing it internally and not calling the libc function sprintf. So if you go on the stack and look at the buffer, destination buffer, you will see that the sprintf results is actually correct. We formatted the string. But what is more interesting is that if we go and look for the arguments on the stack, we'll see that BinCAT was able to recover some type information. So here are the sprintf args, and if you put the mouse over the address of the pointer, you get that it's actually a pointer to a character string. So that's the destination buffer. Here we have the second argument, which is the format string, which is also a character string. And the last one is the variable arguments that are passed to a sprintf. So if we are able to recover the types, of course, we are able to recover the type of the return value, which is the number of characters as a signed 32 bits integer. And so if we go back to the main functions, at the end, we have something interesting. We have an indirect call. So here, the code is calling a pointer that is stored on the stack. So IDA is completely lost because it cannot do value tracking and value analysis. So it doesn't know what value could be there. But BinCAT actually saved the value in memory and could recover the value of the pointer. So if you go to the list of nodes, here we can choose the next node, which is actually the called function. So if we go there, we see that it's the bad guy printf that says bad serial. And here we also have a printf and that displays the wrong serial. And it's as the sprintf that we had before, it's implemented in BinCAT, and it outputs the string on the emulated standard out. So in this demo, we saw that BinCAT is able to statically run a binary and do analysis on it. It's also able to recover some types. So you could consider it as a static debugger, for example. But it's able to do more than that. So if we go to the second demonstration, we have the same binary, but to change a bit, we are going to use a valid serial because we are going to take another cut pass. That's just for fun. Here, we want to see what happens when the program checks for the serial. We want to see what is done on the company string that we provide. So what we do is we go to the configuration window, well, to the X view, and then we select the company that we specified on the command line, and we say, taint this and rerun the analysis. So we set the taint to 0xff, taint everything, and then the analyzer runs. So from the outside, nothing changed, but if you look closely, you will see in the data view that tainted data is actually displayed in green. So that's normal because we tainted company. And then we'll see that on the right, what was previously completely gray includes also some green, about green lines, which mean that every line here in green manipulates tainted data. If it's a sub-function call, and if it's green, it means that some instruction in the function manipulate tainted data. So if we go and look closely at the CRC32 computation, we'll go inside the function. And before being able to compute the CRC, of course, we need to compute the length of the string. So you have a reps.ksb usual inline strlen function, which is in green because, of course, we compute the length of the tainted function, tainted string. So the length is tainted too, and everything is passed as an argument to custom CRC32 function. We're not going to the details, but the function returns the CRC in AAX. So if we look at AAX, everything is green. So you compute the CRC of a tainted string, the CRC is tainted, kind of logical. And if you look at EDX, you can look at the least significant nibble. It's painted in yellow. It means that almost all EDX is not tainted, except in the last nibble, you have some bits that are tainted. So BinCAT is able to track the taint at the bit level. And here we could go into the precise output and see which bit is actually tainted. So it was a flag, so that's the last one. And at the end of the function, so we're going to use the CRC, and I'm just going to show how taint propagation works for arithmetic operations. So the first line actually reads the CRC that I just shown from the company, and it multiplies it by the CRC of the name. So the first one is tainted, and the CRC of the name is untainted. So what happens when you multiply something tainted with something untainted? So here you can recognize the CRC from company, 89BB. And when you multiply it with something untainted, you get BA20, so that's just the value. But of course, it's still tainted because when you multiply tainted data with untainted data, you get tainted data. So we here have a taint analysis, and we could multiply tainted data. And we are going to check how the format string formatting is done just before calling SHA-1 function. So right after the sprintf of all the things we have seen in the data flow, you get this buffer that is going to be hashed. And so if you look closely, you can maybe see it, but company on the second line is in green, and the last line with the BA20, which is the CRC that we multiplied, is also in green. So why can we propagate the taint while formatting a string? That's because since we have a re-implementation of sprintf, BinCAT is able to propagate the taint even though we are calling an external function, because otherwise we would have to go through the real functions. So this string is passed as to compute its SHA-1, and we are going to check if the actual SHA-1 is tainted. Thankfully, everything is green. SHA-1 is a hash function. You have bit diffusion, so if you change one bit, everything changes. So if you have a partial taint, probably everything is going to be tainted, which is the case here. And thankfully, the SHA-1 result is correct. It was computed statically, remembered, and nothing executes on the CPU. Then right after, the keygenme formats the SHA-1 string, the SHA-1 result as a hex string. So you have a small loop that will format everything. And here you have a single address which was looped into by BinCAT, so you can select all the different nodes that were created, so all the different iterations. And we're going to see here all the list. And if you will look into the X view and the memory view, we can iterate and see that the string is format byte by byte, still keeping the taint. And so the final string is tainted because the SHA-1 was tainted. So if we go back to the final comparison, you can see on the listing on the right that here you have the string comparison. Everything is in green because we are comparing the string, the valid license, which is tainted, to the one input by the user. And we have the final indirect call, this time to good guy, which says thank you for registering. So the indirect call is the same as before. The value is stored on the stack. IDA is lost, but BinCAT is able to recover the value. So if you follow the call, you land here, and you have the display, thank you for registering. So now we have seen that BinCAT is also able to do data tainting. It does all the other things, but we didn't have time to do that in the video. So how does it work under the hood? How can you use BinCAT? So as you have seen, we use IDA, and all the IDA part is done in Python. And it talks to the BinCAT binary, which is written in OCaml. So don't scream yet. That's a very good language to write such complex tools. So how does the communication between the IDA plugin and the BinCAT binary work? So we create a configuration file that you have seen at the beginning, and we pass it to the remap binary to run the analysis. At the end of the analysis, BinCAT returns the results and the logs. So that's for the local mode where you run the binary, you run BinCAT binary and IDA on the same machine, but sometimes you may want to run it somewhere else. For example, if you need a more powerful machine to run the analysis, or if you're running Windows, because that's easier for us to use Linux only. So we include a web server that allows for remote BinCAT usage. So you can install the plugin on the machine and have the BinCAT running on server. And we provide a Docker image for easier deployment. So how does it work internally? So as I said before, to disassemble, we need to reconstruct the control flow graph. And I'm going to go into the details of how that works in BinCAT. So here you have a partial control flow with already 4 states. And we're going to see what happens at state 4 and while the disassembly and reconstruction is done. So what is included is in a state, everything known by the analyzer at that point. So you have, of course, the EIP, which means where is the instruction situated. The value of AAX, for example, we of course reduce the state for the slide. And you can see here that EAX is 7FFFF, and that one of the nibbles of EAX is tainted, so it's in green. We also have the flags and everything. So everything is passed to the decoder, so the state is passed to the decoder. So we have a EIP, we have the context, the segments, everything needed to read the code. Then the decoder will read the memory, the code memory, to identify the instruction. So here we have a inc EAX as an example, and it will produce the intermediate language that corresponds to the instruction inc EAX. So if we look into detail, you see that the intermediate language actually increases EAX, as you could expect, and computes all the flags that are needed for after computing inc EAX. So those statements are passed to the state generator along with the state, and the statements are going to be applied to the previous state, computing a new state. So state 5 is the result of the statements over the previous state. Here, if we look closely, EIP was incremented by 1, as we had a 1 byte instruction. Then AAX has changed to 80,000, so it was actually incremented. But if you look, you can see that now we have 4 nibbles that are tainted, because since we had 7FFFF, we had a carry, and so the taint was propagated through the carry. So we have 4 nibbles tainted before, we only had 1. The flag was updated. And at the end, we check if the state was previously seen, and if it has been previously seen, we stop. And if it's new, then we continue. Then when you think of it, you know, like, okay, we do the analysis, we can use states. What happens if you have an infinite loop? Well, you have a long loop. Well, it should terminate at some point, otherwise you could wait forever for the program to stop. So thankfully, we have a strong theory, and which helps us to say this will terminate. So we use static analysis by abstract interpretation, which I'm going to try and explain in one slide. Not easy. So instead of operating on actual values, so for BinCAT, we use values, 10 types, and other things. So instead of operating on real values, all operations are done on abstract objects, which actually represent sets of values or taints of types. So for example, the abstract 0 represents the set of values containing only 0. But if you take the question mark that we have seen before, well, a question mark says this can be any of the integers of this size. For the same for the types, we could have type struct, the abstract type struct, which is another approximation which says this is a representation of all the C structs. And we do all the computations on those abstract objects, and the computations that we do must always be an over approximations of the actual ones. So we are going to see an example of how we can approximate loops, which will show you why the analysis will actually terminate. So that's called loop widening. On the right, you have here the loop that we are going to analyze. So it's pretty trivial. While ESI is less than 8,000, increment ESI by 4. And the red point is where we are going to run the states on the left. So on the first state, we have ESI that is 1,000, which least significant byte is tainted as it's in green. And we have its type, which is a pointer to integers. So the idea here is pretty simple. To avoid infinite loops, we're going to look at the execution of the loop and see what changes and what is stable. So here you have a S2 that is crossed, and that's the computation if you were doing it for real. But there, we're going to check what has changed and what is stable. So between the 2 iterations, what has changed is the value of ESI. It changed from 1,000 to 1,004. So we replace it by another approximated value, which is unknown. So we don't know the value of ESI now. But if you look closely, the type hasn't changed and the taint hasn't changed. So we're in a stable. We run another iteration of the loop. So we add 4 to the unknown value. So when you add 4 to unknown, you get unknown, so that's stable. When you add 4 to the taint, then you get unknown, because since we don't know if you have carry or anything, you need to propagate the taint to the whole register. So we don't know the taint anymore, but the type is stable. And if we do the loop another time, we will see that nothing changes, so we are stable. And thanks to 2 theorems, we have 2 properties that are really interesting. So the SI prime sequence is ultimately stationary, stable, so we'll have the same value over time. And this value that we will get over iterating this widening is very interesting because it's actually another approximation of the real execution trace. So if you say ESI is unknown and the taint is unknown, if you take any actual state from the execution, it will be in the set of the abstract state. So that's pretty neat. It means that you will not have to wait forever, but of course you lose precision, because at the end of the loop, you're like, I don't know the value of ESI. Thankfully, we have some techniques that allow for better precision, but we don't have time to present them right now. So what's really nice is that we have a theory that says everything is going to be correct, even though it's maybe over-approximated. In theory, the implementation should be correct, but if anyone has tried to do an x86 decoder in their life, they will know that it's really, really painful and that you will get a lot of bugs. So the decoder is complex, the abstracting operations are complex, so what we try to do is do a lot of unit tests to validate that the actual disassembly and value computations are correct. So we run BinCAT versus a real CPU, you compare the results and see if we get the same results as a CPU does. So we have our over 67,000 tests. And we also run BinCAT over the QEMU test binary that is used by QEMU to verify that the way they implement the instructions is correct versus the CPU. So we use that, and that's pretty cool. So you may wonder how fast the analyzer is. So on the toy example that I showed before, the Kijinmi, it takes 6 seconds to run 80 megabytes of RAM. That's about 1,000 instructions per second. And on the QEMU test binary, which is way more complex, we got more than 200,000 instructions, a little bit more than 2 gigabytes of RAM in 23 minutes. So you have seen what BinCAT is about, what we can do. What are we working on? So that's what we had, and what we have right now, and that's what we're working on. So we want to have a better type reconstruction. We would like to be able to, for example, look at the accesses on the stack and recover the different fields of a structure that could be hinted by heuristics. One very important feature that we are going to add is, for now, we only have one taint source. So for example, in the toy example that we had, if you took the company and the name and tainted them at the same time, in the end, you will get a result and it would be like, I know this is tainted, but I don't know if it comes from the company or if it comes from the name. So we are going to add several taint sources so we can run one analysis and have follow different data flows at the same time. We are going to refine the computation for backward analysis. We'll also model more standard library functions like sprintf or other ones. And we want to also improve the user experience by adding new functions in the IDA plugin. So for example, the configuration that I copy-pasted for ArcCRV, we want to add a way for the user to directly define the memory into IDA by clicking, for example, on the arguments and say, hey, I want to define this argument in BinCAT. So that's the improvements that we want to make. We also have future features that we want to work on. So we will probably add some finer approximation on value computations. So for now, we use bit vector to represent the values of registers and memory, and we could use, for example, intervals to be more precise in some values. One goal is to also add C++ object reconstruction, which would be awesome. And we also want to add some things on the decoder side, and we want to add ARM and x86-64 decoders. So you have the full paper that is linked here. The link is quite long, so you can find it in the README if you want to read it. And you can get it on GitHub right now or running from Docker. You have a full tutorial in the doc/tutorial.md that corresponds to the example that I've shown. You also have the videos that I've shown, so you're ready to use it. Thank you for your attention. If you have any questions, I'd be happy to answer them.
Hi, nice presentation, nice project. I would like to know how can you scale, interpretation of real applications?
So the idea of the project is not to be able to analyze whole applications. The idea is to really have something that is usable directly by the reverser integrated into IDA. So for example, if you reach a function that is too complex to analyze, but you want to see, for example, and take the input and see where it goes, you can do it from with BinCAT. One of the points is that most of projects of abstract interpretation try to solve the world, and it doesn't work. So the idea is really to interact with the user. So for now, we don't have much interaction, but we sometimes, the goal is to, when the analyzer doesn't know what to do because it's lost, because it has too many possibilities, it's to ask the user, so do you want to remove this option, for example? Because you know that's an error pass that is not interesting. And so the idea is to help the analyzer, help the reverser, and not have the analyzer do everything.
Second question, can it handle dynamically load libraries?
So if you map the library in the address space that is known by BinCAT, you can, of course, run the analysis on the actual code, but you will get probably an explosion of the number of instructions to analyze. So the idea is more to create stubs for external libraries if you can model them. Or if they don't have any side effect, you can just ignore them. By default, it will just skip over imports.
Thank you.
Yes, which domains are used to model memory, and which algorithms and/or domains are used for type reconstruction?
So unfortunately, Sarah is not there. She's the one who actually did all the very complex abstract interpretation part. So the domains for values are vectors of bits, which use 0, 1, or top as a value. And the type reconstruction, I'm sorry, I cannot help, but it's detailed partially in the paper, or you can send an email to have more details.
Hi. Do you handle taint propagation to flags? So if you have a branch that's controlled by on a compare of a control value?
Very, very good question. So the tainting is actually only data flow in theory. So what we did is for conditional moves in Intel, if the flag is tainted, we taint the destination. But for complex things like big ifs then else branches, if you taint because the flag is tainted, you will probably reach like over tainting very quickly. So we haven't implemented that yet, but what we want to do is actually allow the analyst to tell BinCAT if he wants to taint all the instructions that are in a branch. So that will help cover the mix between data and control flow, which is not a problem that is possible to solve in general.
Okay, thanks.
Another question over here.
Just going to do one more and then take a break.
So you mentioned that you made an x86 decoder and that you want to support x86 64. Why didn't you use Z?
The answer is simple. The project was partially financed initially for a part of French DoD, and their requirement was x86, so we started with x86. That's all. And we didn't have time to add 64 bits yet. Thank you very much.